Awesome. Hello, everyone. Good evening.
Wait. Are you recording to cloud? Just check this.
Oh, yes. I wait. Yes, cloud. Yes.
Okay, cool.
Okay. Okay. Good evening, and I'm very excited for today's session. Um. So I was thinking we could start with a puzzle. It goes like this. Let's say you have a lot of water. It's been raining so much here, so we have a lot of water, and you want to sell water to people. But the thing is, the catch is that we have containers of, let's say, 3 liters and 5 liters. So at a time, you can measure, you can use the 3-liter container. It does not have any markings. If you fill the 3-liter container to the brim, you know that you'll have 3 liters of water. If you fill the 5-liter container to the brim, you know that you will have 5 liters of water. And now the task is to see, okay, let's say if somebody comes and they want 8 liters of water, how will you give them 8 liters of water?
So can
That's
I
pretty
touch?
easy, right? Yes, go ahead.
I guess we'll first measure 16 5 liters, 16 into 5 liters, and then so we'll take out 24 into 3. So I guess that will give 8.
Wait, really? Wait, is there
All
no
we did
faster
is
way to do
give
it?
them like one bucket of each.
Exactly. Yeah. Um, 13. Give 13 liters. Oh, is it? Okay, let me switch my video off for a while. I will turn it on in a while. Is it clear now? Okay, it should be fine now. It's fine now. Okay. Yes, can we do 13? Yes, exactly. 5 plus 5 plus 3. Easy peasy lemon squeeze. Okay. What other complicated thing can we do? How about, okay, 2. 2 should also not be that hard, right? How do we do 2? 5 minus 3. Okay. Okay, now maybe what I want you to do is one of you think of something very complicated and come up with a number and give that number as a challenge to other people. So for example, I'm thinking of 7.
11.
11. Okay, awesome. Can somebody do 11? Okay, 5 plus 3 plus 3. Okay, Harsh, we were able to do 11. Nice. Anybody else has any other challenging? Okay, 20 minus 9
Can I
also
use
works.
multiple?
Can you use?
Can I use multiple fives and threes?
Sure, like you can just take you can take a 5 and, okay, that's a good question. So you have like another big thing where you can pour your water, separate your water and give it to your customer. So if you pour, you can just fill up your 5 liters and empty it in the bag, and then you can fill up another 5 and empty it in the bag and so on. Okay, we have something. Soham says 1. Can anybody here do 1?
3 plus 3 minus 5.
Say that again. 3 plus 3 minus 5.
3 plus 3 minus.
Oh, awesome. Okay.
9.
Oh, 10 minus 9 also works. 5 plus 5 minus 3 minus 3 minus 3. Okay, is there...
तरफ है
Okay, can there a way for a customer to come up with something that's impossible to give?
I mean, since we've discovered that we can give them one, so by induction we can give them like everything.
Induction, interesting. Okay, I don't think we really know what induction is yet. Can you give a different argument, assuming
Yeah,
without
I mean, just
assuming?
like every natural number can be written as 1 plus 1 plus 1 something, and we can give them one, so we can give them every natural number.
Exactly. So if we want to give them x, we can just give them. We know 1 is 2 times 3 minus 5. So if we want to give them x, we just multiply this throughout by x. So this will be like 2x times 3 minus x times 5, right? Make sense? Okay, so this manner we can get any number. Very cool. Let's say instead of starting with 3 and 5, we were starting with some other numbers. How about, let's say, if we had 6 liters and 8 liters? What are the numbers that we can achieve
only
here?
even numbers.
Only even numbers. Can we get all even numbers?
Yes.
Yes. Yes, because we can
Wait,
get
wait.
2.
Okay, so maybe you can quickly explain why. Somebody can quickly explain why.
Plus 8 minus 6 is 2, and then we can get every even number.
Okay, sure. So a nicer way to say it is we know 2 is 8 minus 6. And we can get any multiple of 2 by just doing 8x minus 6x. How about an odd number? How can we be sure that we cannot get any odd number at all?
I guess parity, because any multiple of 8 minus any multiple of 6 will always be even.
Okay, so let's formalize what we're saying here. So what we're saying is if we look at, so any combination that we are able to get using 8 and 6 is going to be of the form 8a plus 6b, where a and b are allowed to be integers or 0, so they can be negative or 0. Agreed? So any combination is of the form 8a plus 6b. But
Can
notice that this
always
is
common too.
exactly. We can take out the 2 and whatever is inside is still an integer. So this always has to be even. Always even. And we have shown that all even numbers are possible. Right? Okay, how about if we had 6 liters and 10 liters?
You can get 2 from 20 minus 18. And then or evens are possible. And then from the same argument as before, only evens are possible.
Right. So we can again get 2 here by looking at 20 minus 18. And again, same argument as before as Atharu rightly said. Yay. Okay, so there is some kind of a pattern that we're seeing here. Does anybody want to be bold and state the pattern that's coming up? Or maybe we should take one more example. Oh yeah, somebody was saying something. Go ahead.
GCD, I guess.
Okay,
That's
can
what-
we make it... Yeah. You're saying what everybody's thinking. Can we make it more formal? So, how do we make it more formal? Let's start with, let's say if we have A liters and B liters. Then what is the claim?
GCD of A comma B and all its multiples can be found.
Right. So then GCD of A and B and all is, let's call it something. Let's say D is GCD of A and B can be made, and thus all the multiples of D can be made. This is our claim. this is not a claim. Like, we have something stronger. In fact, we're saying only B and its multiples can be made. In fact, only B and its multiples can be made. Nothing else can be made, right? Does this make sense? Okay, good. So how can we go about proving this? So maybe we can set this aside for a while. We'll come back to this soon. We can do some more warm-up questions before we come back to, let's say, proving this. So how about some very easy things? Let's say we know that, okay. Does
How
everybody
can
know
we
this
prove that?
notation? Hmm?
How can we prove that the GCD of A and B is represented as A plus BY?
Yes,
How can we?
we'll come back to it. So for now, let's leave it aside for a while. We'll come back to it definitely, I promise. Let's do
Okay,
some.
okay.
Yeah, this was just some like puzzle, and now we have some nice mathematical claim. So let's try to gear up to prove it. So let's try to do some easy things. So does everybody know this notation? This basically means A divides B. So if I want to say this more formally, I say that if A and B are integers, let's say, A divides B when there is an integer k such that B is k times A. This is how I'm going to define divides. Is this notation fine with everyone?
Yeah.
Yeah, ma'am.
Okay, awesome. So let's try to do some easy stuff. Okay, firstly, let's say if A divides B, then A divides BC. Can somebody quickly tell me a proof? Where A, B, and C are integers again. All the variables are going to be integers unless stated otherwise.
So I guess we can write B is equals to K, like as mentioned before.
Yes,
Then we just
And
multiply.
BC is equals to KAC.
Yeah.
exactly. So B times C is going to be K times A times C, but this can also be written as K times AC. So by definition, sorry, A
A times
times,
KC.
yeah, A times KC, my bad. So by definition, A divides BC. Yay, okay. How about if A divides B and A divides C, then, okay, make some claim about this.
B divides C.
B divides C or
B
BC have a
divides
common
C.
factor.
That
B divides C. Okay. Is this true? How will we prove this? Okay. Oh, also, my puppy wants to say hi. Okay, moving on. Interesting claim. So how will we go about proving this? How do we start?
A can be written as KB and A can also be written as LC. So now we can,
Hang on. When A divides B, what do we mean?
then A
We
is
mean,
equals to, sorry, B is equals to K into A.
right. So B is equal to K times A.
And for C, similarly, we can write C is equals to L into A.
L into A. Okay.
Now they both have a common factor A, so now B divides C.
here A must also divide.
Okay, so how many people agree with the argument that because of this B divides C? I think some people don't agree. What was Lavish saying? Lavish, say that again.
I think to prove this, we must also prove that K divides L, which is not necessary. Not necessary.
Right. So we want to show that B divides C, which means we want K times A to divide L times A, right? So, okay, let's take an example. So, Lavish, can you, since you are against this, or anybody else who is against this? Oh yes, I see an example. Aditya is saying 2 divides 4 and 2 divides 6. Okay, great. 2 divides 4 and 2 divides 6. But 4 does not divide 6. Okay? And now where is this argument failing? As somebody, I think Lavish mentioned, if we want B to divide C, we want to be able to write C as B times something. And if that is the case, then we want to write, okay, C should be equal to B times, let's say, some variable, J. Okay, maybe a bad name, I don't know. It's fine for now, J. Then if we want this to be true, then we want L times A. So C is L times A, remember. And B is K times A. So we want this to be equal to K times A times J. But that will only be true when L is equal to K times C. Which might not be true, right? Like J might not divide L. Sorry, K might not divide L. So we can say this only when K divides L. Then only we can conclude that B divides C. So this is not always true, as we can see here. Is this fine? Ashutosh?
Or L divides K.
Okay, what happens if L divides K? If L divides K, then what happens?
C divides B.
Yes, if L divides K, then C divides B. So in fact, we can make this into a lemma. So, this is actually also not true. So let me write that it's not true. So 5x means it's not true. Okay, let's try to make another lemma. Let's say we have B is K times A and C is L times A. So we are claiming that if K divides L, then what?
B divides C.
Exactly. And another, so similarly if L divides K, then C divides K. And this is also not hard to see. We just saw. So let's quickly write it down. So if we'll just show this part, the other part is very similar. So if K divides L, what does that mean?
L is equals to K times J as width of it.
Yeah. So if K divides L, then L is K times J, which means that, so we can replace this L in C. So C is equal to K times J times A. But we know that this is the same as K times A times J, which is the same as B times J. So B divides C. Make sense?
Yes.
Awesome. Okay, any more claims we can make? If A divides B and A divides C, then
A should divide GCD of B and C.
A divides BC.
A divides BC. Okay, yeah. We'll come back to the GCD. So we have yet to define what GCD is properly. We will come back to that. Okay. We have A divides BC. Okay. Quick proof of this. In fact, can we say something stronger?
Better yet,
Yeah.
A square divides BC.
Yes, exactly. So
Linear.
A square. Yeah. This is also, okay, quick proof. Somebody just say it out. Yes, A divides B minus C, A divides B plus C. Okay. Some great claims coming in. Let me write that out. A divides B plus C and A divides B minus C. Okay. Yes. How do we prove this? How do we prove number 4?
So for the fourth one, we can again let B is equals to AK and C is equals to AL, and then multiplying that we get BC is equals to A square KL.
Exactly. Awesome. And what about for 5?
So just B plus C is AK plus AL and just take out A common, so it's A times K plus L.
Exactly.
And similarly for subtraction.
Yes. Okay, everybody fine with this? Awesome. Okay. So now what we're going to do is, so as I said earlier, some people mentioned GCD. So maybe can somebody give me, okay, let me write down a definition for GCD. So greatest common divisor. So definition, I'm going to say that the GCD of A and B is a number D, and when some conditions are satisfied. So the first condition I want D to satisfy is I want D to be a common divisor. The common divisor condition, which means that D should divide A and D should divide B. Fair enough. So this is, I'm going to define this in a slightly different way than usual. What I'm going to say is, for any common divisor, let's say K of A and B, K should divide D. This is how I'm going to define greatest common divisor. Is this fine?
Yes.
Okay. So what we're claiming now, so again, this claim that we had, I'm going to just write it in a fancier way again. So claim fancier. I'm going to say, okay, is everybody comfortable, okay, with set notation? If I use sets, will you be fine with that?
Yeah.
Okay, so consider, so let's say we are given A and B, so A and B are fixed, okay? Now we consider the set AX plus BY, where, okay, given A and B, again integers, I won't be saying they're integers every time. X and Y are also integers, such that, so let's say this AX plus BY, I want it to be positive. Yeah, consider this set. Okay, let A and B also be positive integers for now. Positive integers. Let's call this set S. Consider set
X and Y
S.
be positive integer.
Not necessarily. X and Y are allowed to be negative.
Okay.
I just want them to be in such a way that AX plus BY is positive. So I want you to think about it this way. A and B are the liters, like 3 and 5 that we had taken initially, right? And AX plus BY is like a combination of those. So we're taking X times we're taking A and Y times we're taking B. And we're getting that. Okay. We're getting AX plus BY. So this set S is basically so S is like the set of all combinations that we can make with A liter bucket and B liter bucket. Fine enough?
Wait, but that's not always true if X and Y are not integers.
No, X and Y are also integers. So as I said earlier, I won't be mentioning, but everything I say is an integer. X, Y integers. Okay. All good?
Yeah.
Awesome. So, what is our claim? Our claim is
Cannot
that,
be A or
yeah, sir.
be 0?
A and B are positive. For now, we are considering A and B to be positive, so they're not zero. X and Y are allowed to be zero. X and Y are any integers. Okay. But both of them cannot be zero at the same time because we want ax plus by to be strictly positive.
Or both of them can be necessarily negative.
Okay, so if both of them are negative, then ax plus by will also be negative, right? So okay, this fancy notation is only to make whatever we had earlier. This is the exact same setup as earlier. Just that I want to write it in a more mathematical manner. Because why not? So what we're doing is we have A liter ka bucket, B liter ka bucket. We're looking at all the combinations which give us positive water at the end. That's all we're doing. So if you're allowed to take out some water, which means you're allowed to have X and Y negative also. Do you want me to take an example? Would an example be nice? So if we look at, let's say, A is equal to 6 and B is equal to 8, like earlier, then what is happening is we are looking at ax plus by, all the numbers of the form 6x plus 8y, which is basically all the combinations that we can make with 6 liters and 8 liters. So what are all the combinations? So s will be equal to 2. We know that we can make 2, right? Because 8 minus 1. So the fancier way to write it is 8 into 1. So, okay, 6 into minus 1 plus 8 into 1. That's how we can make 2. Then we can make 4 also. How can we make 4? We can do it by 6 into 2 minus plus 8 into minus 1. One way to make 2. Sorry, 4. And so on. So basically, and as we concluded earlier, this set is just the set of all even numbers. 2, 4, 6, 8, dot dot dot. Right?
Yeah, you have said earlier.
Sorry?
You say this earlier.
Yes, exactly. So I was just trying to give an example for how this fancier notation is basically the same as what I was trying to say earlier, what we were trying to say earlier. Fine enough? So what is the claim that we are making? We are claiming that if we look at the smallest number in S, so what is the fancier claim? So the smallest number in S, okay, this is also currently sort of ambiguous. We'll come back to it, why it is ambiguous. Is the GCD of A and B. That is our claim, right?
Yes.
Okay.
No.
Okay, so firstly, why is this ambiguous? Because why is it obvious? So S, my set S could be empty, right? So firstly, we have to verify whether or not S is empty. And then we can talk about the smallest number in S. Also, like
We
a fun
can
fact.
prove that S is not empty.
Yes. Okay, Aritra, I'll come right back right to you. So keep it with yourself for just a minute. So why are we even allowed to like take a smallest number? So there's a very nice principle called the well ordering principle, which allows us to take the smallest element. So what all it is saying is any subset of the positive integers has a least element. Okay, this might seem obvious. Any non-empty subset of the positive integers has a least element. This might seem obvious, but it is very powerful. It allows us to do a lot of things. Okay, so that's what we're invoking here. So we're saying by the well-ordering principle, as some people like to call it, the warp. So by the warp, we'll be using the warp, but for that we need S to be non-empty initially. So Aritra is going to help us with that. So why is S non-empty, Aritra?
I am saying that we can assume that with loss of generality, A is greater than B.
Okay, so without loss of generality, let A be greater than B.
And like X is bigger than Y, and we can say that like X is a positive integer and
Okay,
mod X greater than mod Y. So Ax plus By should be greater than equal to 0, and that proves our claim.
okay, that's a great approach. But there's a much simpler way. Does anybody else want to say it?
If A and B are positive and we let X and Y are positive, then it will be greater than 0 always. If X.
Exactly. So we need to show is that we need to show S has at least one element. That is all we need to show, right? That's enough. Even if I say, okay, look at this element, it's an S. So S is non-empty. Ha ha ha, I'm done. Okay, that's all I need. I don't even need to show S has infinitely many elements. Even if S has one element, it's non-empty. So give me one element of S that is non-empty. Anyone? I'm sorry, give me one integer that is an S.
A plus B.
Awesome. So A
GCD
plus
of A
B
plus
is an S. Does S is non-empty. Okay. Also note that all the elements in S are strictly positive, so it is a subset of the positive integers. So since all elements of S are positive, S is a subset of the positive integers. Yay! Now we can invoke the holy warp. Oh, no, this must think so. Wait, hang on. Okay. By the warp, S must have a least element. Yay. Okay, that's progress. That's progress. So now, okay. What do we need to show? We need to show that. So we need to show that this element. Okay, let's call it. What do we want to call it? Let's call the smallest element G, because why not? Also, do not. Anyways, let's call it G. What do we need to show? We want to show that G is equal to the GCD of A and B. What does that mean? So recall that we had two conditions for it to be this. Okay, Aryan Das, I'm going to mute you because there's some noise coming from you. Okay, you muted yourself.
Yeah, sorry.
No worries. Okay. We want to show that G is GCD of A and B, which means we want to show two conditions. Can somebody remind me of the conditions?
We can show that G divides GCD of A and B and GCD divides G.
Sure, but like we can just directly, okay, that's one way to go about it, but we can just look at the definition of GCD. And if we show that G satisfies this, then we are done, right?
Yeah.
Okay, so also, okay, nobody really called me out about it, but how do you know this is a legit definition? Like, how do you know that for any two numbers A and B, some GCD exists? And further, it also noticed that I'm calling it the GCD, which means I'm saying it is a unique number. Like, you can't just believe me like that. I could be bluffing for all you know.
Because if prime factorization is unique, so there will be a unique number.
Oh, why is the prime factorization unique?
Saee Didi, isn't it D divides K, not the other way around?
Really? Okay, let's take an example. 8 and 12. So what is the GCD? So we already know the GCD is 4. And what do we want 4 to satisfy? We want 4 to be a common divisor. 4 divides 8 and 4 divides 12.
What was I thinking? Never mind.
Okay, no worries, no worries. So let me just complete the thought process. Look at some common divisor of 8 and 12. 2 divides 8, 2 divides 12, and 2 divides 4. Okay, so this seems to be consistent. But the question is, how do you know I'm not bluffing? Like, there are two things. Firstly, you need to show that there exists such a number. Like, I'm just giving you some definition, and I'm saying, okay, call it the GCD, and I'm going to use it in this fancy theorem that I'm proving. But how do you know this even exists? And okay, let's say somehow we show that it exists. How do you know it's unique? Because I'm saying the GCD. How do you know there aren't two of them? How do you know there aren't three of them? Maybe like taking, yeah.
If there are two GCDs X and Y, by property 2 we get that X divides Y and Y also divides X. So hence we have that X is equal to Y.
Okay, that's not necessarily true. Okay. Should we continue this discussion? Maybe we should. Okay, we'll come back to the fancy theorem in a while, guys. Let's first see why. Let's try to see if I'm bluffing or not about the GCD. So maybe I'll just go here. Am I
We can
bluffing?
we can
Does
I think
yeah.
so
Yes.
we can define the set of S as the collection of all common divisors of A and B, and so let the general representation of an element in S be K. Obviously, S will be non-empty as K, one divides both A and B. Then define the set S equal to 1 by K. So obviously, by using the well-ordering principle, there will exist a minimum element because the set S equal to 1 by K is also not empty, and that by definition is GCD.
Okay, we'll go through that. So you defined a set to be 1 by k, where k is a common divisor. Is that what you did?
Yes.
But you can't
And-
use, but can you okay, you can't use this version of the well ordering principle. It's only by a subset of positive integers.
Okay. But
I
it
mean,
should be countable, right?
that,
I mean,
yeah, like sure. And with a lower bound, like if it has a lower bound. So
yeah.
you can generalize this to, okay, so for people who are interested, you can generalize this to any subset which has a lower bound. Okay, like the fancy version is any set which has a lower bound has something called as the highest lower bound of a sort. But okay, we will not be getting into that. We don't want to.
Actually, all I need is that S is finite. So the set S equal to 1 by K is finite.
Sure.
Obviously, so
Fine enough.
it will have a minimum value, and that can be called as the GCD. And then to prove that every K less than every other K, which is a common divisor, divides the GCD D.
Okay, wait. Let's go step by step. So firstly, let's show that it does exist. So there has to be some number which is a common divisor so that every other common divisor divides it. So what Aditya is saying, Aditya, right?
Yeah.
Look at the set. Okay, let's call it something else. I don't want to call it S again. Say P maybe. Is P a good name for a set? I do not encourage following my naming conventions. Okay. Of common divisors of A and B. So P is basically the set of all numbers T such that T divides A and T divides B. Fine enough? Okay. Now the claim is that this set is finite. Why is Why is T finite? Can somebody who's not a Aditya give insight about this?
If it's infinite, then there will not be the greatest, no? Like,
I mean, we want to show that there is a greatest. So that is why we can't assume that there is a greatest.
T is less than
After we
because
ANP
T
doesn't
is less
divide.
than equal to A, and there are only finitely many numbers less than equal to A, so T has to be finite.
Right. So the absolute value of T is less equal A, right? So, okay, maybe we can add this to our set of lemmas that if we have, let's say, if T divides A, then absolute value of T is less equal A. Absolute value of A. Maybe this you can take up as a homework exercise. But do you like at least intuitively you should be able to see that if one number divides the other number, the like if T divides it, then T has to be smaller than A, clearly.
or
So
a
sure. Okay. So T is A, so only finitely many options. Okay. Okay, good. So we know T is finite. Now what do we do? Now I think somebody Atharva, did you want to say something?
Oh, my mic is on, sorry.
Okay, no worries, no worries. So what was somebody saying? I think Aditya was saying that if you look
I
at the
was, yeah,
if you look at so
sorry.
since it is finite, we can always just look at the largest number. So Aditya, we don't even have to do the 1 over thing. Like since it's finite, we can also claim highest number. So
Yeah, I just wanted to apply the well ordering principle that's you mentioned.
yeah, sure, fine. So thus there is a largest element in T, right? Let's say, what do we want to call it? Call it. I'm running out of nice variables. Give me some nice variable names. What should
Z.
we call it? Z. Let's go. Okay. This is like, okay, fine enough. Call it Z. Now, what do we want to show? So, we already know Z is a common divisor, right? Because Z belongs to T, because a Z is an element of T, Z is a common divisor of A and B. Now we also claim, so okay, what Aditya is claiming, not me, Aditya is claiming that Z is actually the GCD, which means for any common divisor, K of A and B, K will also divide Z. So let's write this. Aditya is claiming any common divisor, let's say K of A and B, uh, of A and B also divides Z. Okay, do people see why this is true?
Yeah, so basically you can consider the prime factorization of all the other elements of the
One
set
minute, one second, one
E.
second. What is
Yeah.
prime factorization? Hang on. What is prime factorization and why does it exist and why is it unique?
Okay, so basically primes are those numbers which are only divisible by itself and one. So there are no other. Okay, so I think the definition of divisor is already said by you, DV. So how can you clarify on that? The
Hmm.
prime factorization basically claims that there's only one and unique way to factorize or form the divisors of a number. And that is by using building blocks called primes raised to a particular power. By that, I just mean multiplied by itself several times. The reason why it's unique is considering so suppose there are two different prime factorizations of the same number, and suppose so there are two cases. Suppose a prime p appears in one of the factorizations but not in the other, then because they're equal, p should divide the other side. But since there's no because the definition of p itself states that it only divides itself and multiples of p, there's no other factor of p on the RHS, so that's clear contradiction. And also, if you have the same prime on both sides, but at different powers, then there'll be you could do the same thing. You just cancel R
Okay,
prime is
so
larger, and then
okay, okay. So you've shown why it is okay. Is this an internet issue at my end? Can you still hear me properly?
yeah, I can hear you properly.
Okay, okay. So you've shown that if there is a prime factorization, if there's a canonical prime factorization, then it's unique. Sure, but okay. So the thing is, like, the proof of this is not that obvious. Like, it's a couple of pages long, as far as I know. So maybe let's not assume prime factorization for now. Can you do it without using prime factorization?
I
Oh, I
think I
have
have to
something.
think. I think I
Okay,
have
okay,
to think then. So I'm sorry.
okay.
So can we say that K also belongs to D, and K is less than equal to Z, and so as K belongs to K, it will also divide A and B, and hence as K is less than equal to Z, it should divide Z.
Okay, so we have okay, I agree till K that's equals Z, but why does it imply that K divides Z? That I'm not sure I understand.
No, actually, doesn't K belong to the set T?
Yes, K is in T. So here we are letting Z to be the largest number in T. So Z is not the GCD. Z is the largest number in T. And the definition of GCD is this. So we want to show that Z is GCD by this definition. So do you see what the problem is?
Well, I've got a question. So when we say that K of A and B, that means that K divides A and K divides B, right?
Yes, so we are saying K divides A and K divides B.
Hence, K should
So these
belong
are
to
the
the
things.
set T.
Yeah, yes, we know that K is yes, K is in T, sure. Thus we know that K is less than or equal to Z. That also I agree. But how can we conclude from here that K divides Z as well?
We need to show that K is equals to Z is equals to some Kx, but we are not getting that. Yes.
I just wanted to ask. So by prime factorization, we could just claim that the prime factorization of K would just be a subset of Z, and then we would be done. But I don't think we're allowed to use prime factorization. Is that
How about
basically?
proof that there's only one, there can be at most one GCD?
Okay, let's take a
So,
look at that.
so go back to
So
the definition of GCD.
1 second, uniqueness.
So, let's say you have two GCDs, X and Y. So we know that X is a
Yeah,
common divisor of A and B. So is Y.
that X and Y are both GCDs of A. Then we know that X and Y are common divisors, sure.
Yeah. So, by property 2, if X is a GCD and Y is any other common divisor of A and B, we know that Y divides X.
Property 2, Y divides X, sure, I agree.
And similarly, we have X divides Y because Y is the GCD and X is a common divisor of both A and B. So we get that X is equal to Y because X divides Y and Y divides X.
Okay, there's a very small catch. I just want to see. Can anybody see it? Because I did not explicitly mention this one small thing anywhere, which might like lead to two GCDs.
It's
It can be
actually
negative.
it's mod X equal to mod Y.
It can be negative.
Exactly. So I need to mention that. Okay, we'll for the purpose of this, we will also be assuming D to be greater than 0. So
So we get
yeah,
X is equal to Y. And a common divisor of X and Y clearly exists. So Now we all
Okay.
need to show that the greatest common divisor, all other common divisors divide. There exist common divisors that all other common divisors divide that common divisor.
Right. Okay. Okay. Maybe should we also like keep this aside for a while? We've been trying this for a while with no progress. Maybe it might be a good idea to look at just assume this definition for some time. Maybe try to do this for a while and maybe come back to this in a while. Or if anybody has any other ideas for this, we can try this more for a while.
I also have the same idea like Aditya. Through prime factorization, we can show that GCD is unique.
Yeah, the thing with prime factorization is that it's slightly okay. That's definitely a proof. Maybe can we find a proof without prime factorization? Is what I was thinking. Because prime
I
factorization
have a
itself is
property.
not easy to prove. Like it's some like as far as I know, the proof for unique prime factorization is some 2-3 pages long. So we don't want to go into that.
No, I
I
can
have a
say it.
property. Ma'am, I have a property which can prove this.
Okay,
Can I say the property?
sure.
The GCD of XA, comma XB is equal to X times the GCD of A and B.
Okay, and so how will we use that to prove this? Okay, I think there is some way to prove this. Like, okay, let's say that k does not divide z, then can we somehow look at the lowest common multiple of k and z that's going to be greater than z, and that is also going to be a common factor of a and b. So that's the intuition that I'm going for here. Maybe we can try this after a while. Like, okay, now I'm defining more things like the lowest common multiple, etc., etc. But
We have
we
Z is
can.
equal to A dash.
Sorry,
Can we
I
use
can we use?
Euclid's division lemma?
Sure. Okay. That's not as hard to prove as the prime factorization. So how will you use Euclid's division lemma?
We have to prove that the GCD exists, right? I'm just confirming.
Yeah. Like so, we want to prove that the highest element of this set T is also the GCD using this definition, which means if we consider all the common divisors and if we consider the largest of all these common divisors, then any other common divisors is going to divide it, is what you want to prove.
I think I have another method to prove it. So what you can do is you can assume A is equal to ZX and B equal to ZY. So where X and Y are just integers, and obviously X and Y will be co-prime because if they were not co-prime, then there would exist a larger element of the set T. I think that's something you can take for granted by defining this way.
Okay, so when you say x and y are co-prime, you're again saying the GCD of x and y is 1. So like
Yeah.
what definition
So
of GCD are we
we
going for? Like that's sus. We have to be careful here.
okay. Yeah,
Okay,
can I define the
using you say first.
Yeah, Aditya?
yeah. So sorry. Am I allowed to say that X and Y uh, have a GCD as one, or is it not? I mean,
Like you have to be careful now. So what definition of so now GCD 1 you mean that if we consider
yeah,
the set of
the
common
largest common.
divisors.
Yeah.
Yeah, sure. Okay, fine.
So I think
So
that's okay. X and Y
Okay.
have their GCD as one. I like one is the largest set element in the set T of X and Y.
That should work. I think yes. Otherwise, then we can always, so Z won't be the largest one for A and B. Fine enough.
Yeah, exactly. So you can consider any other element, suppose K belonging to or T belonging to capital T. Then
Okay.
so obviously T is a common divisor. So we can define A and B. So not A and B. Let's take something else. C and D, such that TC is equal to A and TT is equal to B,
Okay.
and B is equal to T. Yeah. So clearly, and so obviously A is equal to ZX as well. So we have the equality ZX equal to TC and ZY equal to TT.
Okay.
Yeah. So now consider clearly T will divide the LHS of both the equations. And so suppose T does not divide Z. So that by definition means that T would divide X and T would have to divide Y.
No. So okay, maybe this should also be another lemma. Okay. Let's see why it is true or why it is not true. So what
Okay,
Aditya is
I
just claiming
guess,
right now
yeah.
is A divides BC and A does not divide B. Can we conclude something?
A divides C.
A divides
A
C.
divides C.
I guess
Okay.
that's wrong.
No,
If
we cannot
we can
say
only
this,
say
I
that when
think.
A and B are co-prime.
So I can give a
Okay,
counter.
a lot of good things coming up. Yes, give a counter example.
14 divides 2 into 21, and
Okay, wait, do you not have smaller numbers? This is too much for my small brain to process. Smaller numbers, smaller numbers. Like some one-digit numbers.
I have shared my idea in the chat.
4 divides 6 into 2,
Like
4
4
divides
divides
6 into
6
2.
into 6. But
and 4 does not divide 6, but we cannot
Divide
consider 4
6.
divides 2.
But 4 does not divide 2 either. Okay.
Yeah, I see my mistake. Thanks for pointing out.
Okay. Aritra has sent something in the chat. Zx is A and Zy is B. Then GCD of Zy and Zx is Z times GCD of X and Y. Z is a common factor of AB. GCD AB is T. Therefore, Z divides T. No, I don't see it. Can you unmute and say it?
Because T by Z is equal to the GCD of X and Y, and the GCD of X and Y is an integer, then it's divided.
No, I couldn't get that. Sorry. Do you want to go step by step? Okay, Zx is A and Zy is B. I'm fine till that. What do we? And Z is the
Yeah,
common largest, like Z is the maximum element in this set T. Okay, fine with that. What next?
I am assuming that Z is an integer and T is the maximum element.
Okay, you're assuming T to be the maximum element and Z is some common divisor. Okay, let's stick with this notation, right? We have Z
Yeah,
to
yeah.
be the maximum. So let's say Z is the maximum element and T is the thing. Okay. And T is a common divisor. Then what we want to show is that we want to show T divides Z. So how are you showing that T divides Z?
I take the GCD of TC and TD. And this is T times the GCD of C comma D.
Okay. So you're taking the GCD of TC and TD. That's T times the GCD of C and D.
And
I
the
see.
GCD of TC and TD is the maximum element of the set, which is the GCD. Yeah. Then
Does this work though? Let me think. Yeah, this should be fine, right? So what we're doing here is, okay, let T be a common divisor. Then we're looking at TC and TD, the GCD of TC and TD. And whatever the GCD of TC and TD is, T has to divide it. But then again, why is that true? Why does T have to divide the GCD of TC and TD? If you're claiming it's because of this.
because this is
But if you're
easily can be
defining
proved.
GCD, like if no, like it's very sus right now. You have to be very careful. Like over here, which definition of GCD are you going by? If you're going by this GCD, then this is a non-trivial statement to make, I believe. So I guess a lot of us are on the right track. We just need to finish it. So we only have, like, we have less than 30 minutes left. So maybe I would prefer if we, like, I'm pretty sure, like, we can finish this together. And then if we still have some time at the end, we can come back to this. This is not that hard as well. But my first priority would be finishing this. Would that be okay? Also, somebody, I think it was Aritra, you see why we have to be more careful over here, because we're jumping between two definitions of GCD, and we can't just use one definition to prove something and then the other to prove something else and then combine them together and so on. Okay.
We
All
can
right,
use
let's get back
the
to.
Euclid's division lemma to prove that GCD exists.
Okay, sure. We will. I was also hoping to get to that. Yeah, thanks for reminding. So let's quickly finish this and then go to
Yeah,
Euclid's algorithm. That also I want to talk about. Okay. Yeah, thanks for reminding. Okay.
can use the Euclidean division lemma.
We will get to that. Sure. We don't know what it is yet, and for now, let's just be fine with this. Let's try to complete this. So we want to show that G is the GCD using this definition. Wait, this definition. So we need to show three things. Okay, G is positive, that we already know. Okay, let's do a recap. So what we were doing is we had this fancier claim that if we have this set S of all linear combinations of A and B, all combinations of A and B, all such that they are positive, then the smallest element is going to be the GCD of A and B. So firstly, we showed that S is non-empty, and thus there has to be a smallest element. Sorry, so thus there has to be a smallest element by what? Yes. Let's call G to be the smallest element. Now we want to show that G is the GCD of A and B. So firstly, we need to show two things. One is that if we, okay, it's a common divisor of A and B. We need to show G divides A and G divides B. And secondly, we need to show that for any common divisor of A and B, K divides G. So it is a common divisor of A and B. And secondly, any K divides A and K divides B, then K divides G. Okay, one of these two conditions is really easy. Can somebody tell me which one of it is and finish it off for me? So we know that G is the smallest element of S. So let's also so G can be written as some AX star plus BY star. Okay. Now what do we do? Okay, let me tell you. Second condition is easy. Can somebody quickly show me why second is true?
A is equal to k into some integer, b is equal to k into some integer, k comma.
Exactly. So k divides a, k divides b. In fact, we can also add it as a lemma here and directly quote it. So like we can extend this lemma 5. In fact, a divides anything, bx plus cy. So by lemma 5, 2 is immediately follows from lemma 5. Okay, fine enough. Now we want to show that g divides a and g divides b. That is slightly trickier. It's not immediately obvious, right? So this is a very neat argument that I really like. So let's say a is equal to let's say that say g does not divide a. What does this mean? This means if we divide a by g, then there'll be some remainder, right? So a is, let's say, g times q plus r. Okay, this is also I'm going to do a star star star. Maybe I'll put this in the p set to show that this is true. Where very important, r is less than g. 0 less than r less than g. This is just the, what is this called again? I forgot. This is just the, there's some fancy name to this.
Division
Is this, yes, so right, it's just okay, my bad. Okay. This maybe can be in the preset, or if there's time towards the end, we'll prove this, or it will be put in the preset. So a is gq plus r. Right, now we can substitute this here. So now what my claim is, see, it's very suspicious here that r is less than g, and we are claiming g to be the smallest element here somewhere, right? Yes. We are claiming g to be the least element of S. So if we somehow show that R is also an element of S, so the intuition is that we now have R less than G. So if we can show that R is also an element of S,
I guess
then
I
we
got
will have a
Yeah, we easily
contract.
can by substituting g
right.
equals ax star plus by star.
Exactly.
Yeah, we can write r is equals
So,
to gq and then
so
substituting.
star plus by star times q plus r. This is simply by substituting the value of g. Okay, let me write that. Substitute value of g to get this. Oops, yeah. And now we can rearrange some terms to get r is equal to a minus ax star q minus by star q, which is just like a times something, 1 minus x star q plus b into minus y star q, which is again of the form a times something plus y times something. And also note that r is positive. So we have all the conditions of S satisfied. So r does indeed belong to S. But that's a contradiction. Let's go. Nice. Neat. So now we have that G has to divide A. So G has to divide A. Or another way to think of it is that R has to be equal to 0. So similar argument. Similarly, G has to divide B as well. So both conditions. Oh, wait. I can't spell. Conditions for GCD satisfied. Yay. G has to be the GCD. Neat. Okay, so one thing we can do now is we can be clever. So okay, so wait, before I go on, any questions, anything you want me to repeat? Okay, good. Maybe I'll wait like 10 more seconds. You can look at my puppy till then. I'm not sure if you can see her, but okay. Anyways, good. Something in the chat?
Okay, so
Okay, good question, Harsh. One second, Sharanya. Sorry, I'll come to you, Sharanya. So this is the Euclidean algorithm, that something that we learn in like third grade or something, I don't know, is that if we have a number a and if we have another number g, we can divide a by g to get a remainder r, which is smaller than g. Right, Harsh? Do you agree with that? Yes. And here we are assuming r to be positive, strictly greater than 0. Why? Because if it was exactly equal to 0, then g would divide a. Make sense? So that's why r is a number that is not 0, so it's positive, but it's still less than g. And it still belongs to S. But that's weird because the definition of G is that it's the least element of S. We cannot have a number, positive number less than G that is an S. But I just showed you a positive number less than G that is an S. Make sense? But I was assuming the fact that G does not divide it. Okay, cool. Okay, cool. Sharanya. Okay, right. That's exactly what I was coming to. So now what I'll do is so I know that I'm going to make my definition of GCD, okay, which is okay, very sus, but okay, I would really encourage you to go back home and think more about this. I'm going to say, okay, here is my new definition of GCD. It is that if you're given A and B, consider the set S and consider the least element of the set S, and that is going to be your GCD. That is how I'm going to define GCD. Okay, maybe let's like give it a new name. Let's call it like HCF. I'm going to define HCF to be the number, and you know it exists because S is non-empty and S has to have a least element by walk. So the HCF of A and B is going to be this number, the smallest element of S. HCF. I'm not sure if you people have like heard this abbreviation. It's also like highest common factor. That's how I'm going to define that. And now using this definition, can we show this definition? What I mean, let me clarify. So if I have, so can I show that the smallest element of S is the largest element in T that we had defined earlier? T is the set of common divisors. What am I saying? Maybe this might be easier. I don't know. Let me think. Yeah, this shouldn't make sense, right? Because if we consider, let's again going with the same notation, G is, let's say, ax star plus by star is the smallest element. Now, as we know, G has to belong to T. G is in T because we know it, we have shown that G divides A and G divides B. And we want to show that any other common divisor of A and B is less than G, right? So can somebody quickly tell me why? Any common divisor of A and B is less than G. Why?
Didn't we did the same thing in property 2 of that proof?
Yeah. Also, can you all just think and confirm that I'm not making a loopy argument here? I just want to make sure. Is this a loopy argument? I don't think so. I think it looks fine to me. So if K divides A and K divides B, like let's say, so say K is an element of T. So K divides A and K divides B, which means, so thus K divides A and K divides B, which means K divides J. So K less than J. So G is the largest element of T. So all of these three definitions of GCD are equivalent.
Well, I've got a question. So, if K divides C and K divides B, how does it imply that K divides G? Like, is there a proof there?
That's because of this. That's because of this. Okay, let me call this 1. This is by 1. Make sense? Because you substitute K divides A and K divides B. So, okay. Any other questions? Okay, awesome. So, a very cool exercise. Now, let's get back to another thing we were trying. Somebody, I don't remember who. Like, can we salvage this? Okay, this seems like this should be true, but it's not true. But can we come up with something that is true, that is similar to this?
If GCD of A and B is 1.
Exactly. So let's salvage this and say A divides BC and GCD of A and B is 1. Then what are we saying?
A divides C.
Okay, can you prove this? This is a very cool and very fun exercise. How will we go about proving this? Maybe let's think about it for a while. If you have any ideas, maybe don't unmute and say, just share it on the chat. Maybe.
Load screen is visible.
Who was it? Sorry, my internet is not okay. Yes, can you say that again? Somebody was saying something and I couldn't hear you. Yes, Lavish. Lavish, that is exactly right. But why did you send it to everyone? No, I'm sad now. Okay. Soham, that is not right. So we will discuss that also. Is that third was still here? Yes. Okay. Now let's get back to what Soham is saying, and then we'll discuss what Lavish has sent. Okay. So what is Soham saying? Soham is saying GCD of A and B is 1, so A does not divide B. But A divides BC, so A divides C. So that argument is not right because we saw this example, right? 4 divides 6 times 2, but 4 does not divide 6. But that does not imply that 4 divides 2. Do you see that, Soham? So it is not enough to say that if A does not divide B, then A divides C. We have to use a much stronger condition, which is that the GCD of A and B is 1.
My proof is correct now.
Was that Lavish?
Yeah.
Yes, that is correct. Also, in the future, avoid sending the proof to everyone. Like when I said send it on the chat, I meant send it to one private chat so other people don't see it. But that's fine for now. Okay.
Okay, I'll take care.
Okay, thanks. Awesome. So let's get to Lavish's proof. So I'll maybe just copy paste this below this. Okay. So we know the GCD of A and B is 1, and we just learned some very cool thing about the GCD. So if GCD of A and B is 1, then there exists x and y such that ax plus by is 1. And this is the starting point. Then you can try to go ahead from here. So maybe I'll also just leave this here because there's one last thing I wanted to say and there's only 5 minutes remaining. Okay. Okay, now one zero nine or something. Okay, the GCD is clearly 1. Find x and y. Find x and y such that 73x plus 109y is 1. How will you do that? Okay, because of this theorem, we know that such x and y exist. But how do you find such x and y?
Reversing the Euclid division algorithm, we can find it.
Let's go. Okay, so since there's like 5 minutes remaining, I'll just say it out. So do you know how there's a way using the Euclidean algorithm to find the GCD? How do we do that? We start with 109 and 73. We divide 109
2 1
73 into just do the calculations. Plus what? 36 is it? Okay, this is not so bad. And then 73 is, so we do this. We divide 109 by 7 and write the quotient, write the remainder. Now what we do is we write 73 here again and divide it by the previous remainder. So we divide it by 36, write the quotient, write the remainder. Right? Okay, this worked out really nice. And now we have that this is the GCD. This is usually how this is the Euclid's method algorithm to find the GCD. Now we can just reverse this in a very, very clever way to like this. Let's say 1 is, so this I'm going to rewrite. The second equation I'm going to rewrite as 1 is 73 minus 36 into 2. But I know that 36 is also something. What is it? 109 minus 73. So I can substitute for 36 over here. So I can say 1 is 73 minus 109 minus 73 into 2. And now I can open the brackets. I can say 73 minus 109 into 2 plus 73 into 2. But this is just equal to 73 into 3 minus 109 into 2. Let's go. So we do the Euclidean algorithm first, and then we do the reverse, and then we substitute.
There is any way to substitute like this?
Okay. Yes, so the substitution is done using this reversing. So first we start with 1, and then, so we started with this. Now instead of 36, we write it in terms of 109 and 73. So let's take one more example. Actually, this was a pretty bad example, bad-ish example, not exactly bad. Okay. Let's take another example. Give me some two numbers, like 3-digit and 2-digit is fine.
44, 36 maybe.
44, 36, okay, fine. Like 3-digit. Give me one 3-digit number.
142.
236.
Okay, 236 and wait, what is that? 236 and let's say 51. So we first divide 236 by 51. What does that give us?
Plus 32. 4 into 4 plus.
Okay, I will be trusting you on this. Now I write 51 as this. What is this? Is this correct? Now I write 32 again. What is this? 13. Okay. Now we get 1. So this GCD is 1. Now we reverse all these things. So let me write this down properly. Euclidean algo. Now we reverse all of these. We have that 32 is 236 minus 51 into 4. Okay, this can somebody unmute and tell me this quickly so we can do this. 51 minus 32. 13 is 32 minus 19. 6 is 19 minus 13. And 1 is 13 minus 6 into 2. Now we start with the bottommost and then we substitute. So 1 is 13 minus 6 into 2. Then we do, instead of 6, we write 13 minus 13. So we have 13 minus, wait, I can't write. 13 minus 19 minus 13 into 2. So that's just 19 into 2 minus 13 into 2. 13 into 3 minus 19 into 2. Then we substitute for 32. Sorry, we substitute for 19, which is, sorry, over here. We substitute for 13, which is 32 minus 19. So we get 32 into 3 minus 19 into 5. Then we get, so I'm just skipping over the algebra, but you can make sure of this later. What do we get next? Can somebody help me out here? We substitute for 19, it's 51 minus 32. So 32 into 8 minus 51 into 5. Then we substitute for 32 as 236 minus 51 into 4. So 236 into 8 minus 51 into 32, 37. I think this should work. So we get this. So we find the values of x and y using this. So x is 8 and this is minus 37. This is how, using the Euclidean algorithm, we can find the x and y. Fine enough? You can, so maybe I'll put some more numerical examples like this in the preset so that you can get a hang of this. But yeah, so more fancy things. So the last thing I'll say before we stop is that these types of equations are called, okay, so equations like ax plus by is equal to c, where a, b, c are given, are called linear Diophantine equations and are usually solved using, and can be solved using Euclidean algorithm as we just saw. So these are, this have, so, okay, there's much more study that you can do here. Maybe that also I'll try to put on the preset. So this 1.5 hours is not enough. For example, there are going to be, okay, how many such xy exist is the first question. And Euclidean algorithm tells us how to find one of these solutions. How do we find the rest? So these are some questions to ponder upon.
The general solution would just be like
Maybe. Hey, no. Okay.
Okay.
Yes. Okay, thanks, Aditya. Okay. Alright, this was really fun. Yes, if a single solution exists, then infinitely many exist. Exactly. Euclidean algorithm only tells us how to find one of them. How do we find the remaining ones, right? That's one question to think about. So that's, I think, what I had to say today. Hopefully I haven't missed out on anything. Do you guys have any more questions or comments or feedback? Just feel free to unmute and say. Otherwise, we'll stop here. Let me stop the recording.